Hello, friends in Iraq and at Mosul Dam. Thank you for giving us the opportunity to present to you today. I, Wade Anderson from the U.S. Army Corps of Engineers Dam Safety Program Manager, along with Georgette Heplis, our Principal Geotechnical Engineer, are going to present an overview of the Corps of Engineers Dam Safety Program, as well as some specifics on data management and evaluation of instrumentation of the Corps of Engineers structures as they continue to operate and provide benefits of flood risk management, water supply, navigation, recreation, hydropower, as well as environmental benefits. The Army Corps of Engineers is often considered the nation's engineer. We provide infrastructure, engineering, construction, and operations for a variety of types of structures throughout the country. But today we're going to focus primarily on our what we call civil works infrastructure, which includes dams and levees, navigation channels. The Corps of Engineers owns and operates over 700 structures as part of over 550 reservoir projects. In addition to that, the Corps of Engineers has designed and constructed over 2,200 levee systems. We operate and maintain 1,200 miles of inland navigation channels. Associated with that navigation is over 200 million cubic yards of dredging annually. We maintain over 900 inland harbors and coastal harbors, provide significant water supply throughout the country through our storage in our reservoirs, and also generate 24% of the U.S. hydropower capacity. Corps of Engineers is a large organization that operates throughout the country as well as internationally. We have over 35,000 employees, 9 divisions and 44 districts. The districts maintain and operate our structures throughout the country, throughout these 9 divisions. As you can see by this map, the Corps of Engineers has dams and levees throughout the country, the majority of them from the middle of the United States towards the east, but also several systems throughout the west and along the Pacific coast. We have over 740 structures, a large population at risk of nearly 13 million individuals. The property at risk is well over $1 trillion beneath downstream of our dams. We do have a wide variety of dams, from earthen to concrete dams. Our levee systems that the Corps of Engineers has built and is responsible for throughout the local sponsors. Population of risk at 12 million again, and over $1 trillion again of property at risk. Most of those are earthen structures designed and constructed along riverbanks throughout the United States. Levee infrastructure throughout the United States is fairly aged. Most of the dams were built, as you can see from this slide, between 1930 and 1980, with the average age of the dams and levees being around the 60-year-old range. That presents a unique set of challenges. Many of them still perform fine, most of them do, but they do require continued maintenance and modification to provide the benefits expected by these structures. Related to dams, there was a federal guideline developed in 1979 that has defined our overall dam safety program that I will speak of in just a few minutes. Just in the early 2000s, the Corps of Engineers transitioned to what we call a risk-informed decision-making, which I'll also present, as well as Ms. Heplis when she talks about evaluation of data and evaluation of performance of our structure. This slide is a summary of our dam safety program. The outer loop in gray with the green boxes is what we call a routine dam safety activities. They include periodic inspections, annual inspections that are referred to as routine inspections. We have instrumentation, we do dam safety training, emergency action planning, emergency exercises to prepare for emergency should we have an incident or a dam failure. The middle box, or the middle line, the red boxes, are activities that we perform should an incident or special event occur, such as an issue at a dam that performance is in question. That activities are included in issue evaluation study, where we would further study that issue, and if the risk were considered to be justified further action, we would do a dam safety modification study and report, which would recommend modifications to the structure to return it back to service, and then at that point it would be in this outer loop again as part of our routine dam safety that includes a variety of activities, some of which Ms. Heplis will talk about following my presentation. As we will present in just a few minutes, the risk associated with a dam is a part of that is the consequences downstream. And this slide just illustrates two of those over 700 projects that have had significant population growth downstream, therefore increasing the consequences associated with the existence of this structure and as it continues to provide the benefits delegated by Congress and through construction and operation of these projects. As I have mentioned before, we have a risk-informed decision-making as part of our dam and levee safety programs. That risk is a function of three things: hazard, performance, and consequences. The hazard being the loading, such as a hydraulic load, a reservoir elevation, or spillway flow, or a seismic loading from earthquake. The second is performance. How will that structure perform? And the last component of that risk is what is the consequence should that dam not perform under that set of load conditions? Is it loss of life? Is it economic? What are the values and economic or loss of life impacts, again, from that load and performance of the structure?
And performance monitoring for dam safety. Data management is critical to our understanding of each project. With the advance of technology and passing of time, a lot of data is acquired and needs to be maintained, accessed, and compiled. The accumulation of all the information is what helps us inform our understanding of dam safety. The more useful information we have, the better decisions we can make. Often, we need a good way to both readily access and communicate that data. With available geographic information system technology and databases, we can readily visualize data in a site information model and use that data in risk assessments, emergency response, and rapid decision making. Part of that data includes performance monitoring data from instrumentation to aid in quantifying performance over time. This instrumentation data is combined with all other known project data to best inform the likelihood of a potential failure mode on a project and to help reduce uncertainty in risk estimates. USACE have developed an approach to data management using site information models that integrates our data in a way that creates a new or renewed understanding of our projects and allows for knowledge management. Here's an example to help illustrate what I mean. This is an existing dam that was undergoing a risk assessment. The team considered 4 different potential failure modes for this project, which are shown in the image with yellow triangles. For this project, all the failure modes were related to internal erosion. One of the internal erosion processes was into the embankment, from the embankment into the foundation. The team wanted to evaluate the risk of this potential failure mode by looking at the geologic formations, foundation grouting information, past performance, and instrumentation. The team geo-referenced a plan view drawing of the original foundation grouting, which you can see in the black dots in this drawing overlaid on the aerial view. This is good data, but it was not useful in this format. The team digitized the grout holes from the drawing, which provided a slightly better visualization. But in addition to the spatial location of the grout holes, the team also needed to understand the grout volumes that were placed in each of these holes. That was then also digitized. Using spatial analysis tools, the team was able to create a heat density map that highlights areas which required the greatest amount of grouting. As you can see, this provides some very good information that would take a lot of effort to be able to understand from paper reports or even a spreadsheet. The team then wanted to understand the relationship between the grout take information and the foundation geology. The team digitized the foundation map that they had available from historic records and was able to make a layer in the site information model and readily overlay the grout take data with the geologic mapping information. And they were able to ascertain the relationship between the grouting and the geologic units. The team then added a layer for instrumentation, in this case piezometers, to show the spatial location of the instruments. The database included information related to the monitoring zones for each instrument, such that they could readily identify which instruments were monitoring which geologic unit of interest, and then get those instrumentation records. That was a very simplistic model, and in many cases that may be sufficient for the risk assessment. Other times there may be more complex issues, or you may want to view the data in 3D. Shown here is a 3D site information model for a concrete dam. This dam was under modification to address sliding potential. Over 500 anchors were installed in this dam to protect against sliding. To track construction and assess the quality of the work during construction, and document the construction data for future risk assessments, this 3D model was developed. As-built drawings and survey data were used to build the model and spatially locate various elements. As you can see, rotating the model, you can look under and around any feature of the project. This provides a good communication tool for any member of the team. The ability to turn on and off layers also helps to visualize specific elements that you may want to see. In this case, this is the anchor data being visualized, and you can see the compressive strength reports for the grout that was placed in the grout in the anchor installation. Additional information can be ascertained by turning on and off different layers. In this case, you can see the water tightness test that was performed, and you can color code the resultant data to best visualize the variability of the information. You could also select different individual elements of the model and be able to see different attribute data, spatial information, and links to different information available, including anchor length, date of install, date of completion, and hyperlink to reports so you can see photos and other available information related to the model. So far, I've only spoken about site information models and access to spatial information and data, but I have not yet addressed instrumentation and performance monitoring. As noted by the International Commission on Large Dams, an instrumentation and monitoring program is essential throughout the life of a dam for a variety of reasons, including assessing the performance during first filling, comparing actual performance with design, and characterizing long-term behavior, providing early warning of abnormal conditions, analyzing responses to events, and demonstrating safe management of the dam to regulation authorities. The U.S. Army Corps of Engineers has an engineering manual that helps districts and personnel implement an effective monitoring program. There are 4 key elements as part of this monitoring program. These include identifying potential failure modes of concern, developing performance monitoring program to address those concerns, implementing the program and ensuring quality management of the program, and then evaluating the data from that program to assess the project performance. A particular emphasis is ensuring that we are placing instrumentation where we think there may be a potential problem or future potential problem. In the past, instrumentation was placed on a grid, and data was being collected that may not have been placed in a location where there was a concern. This is good for general health monitoring, but is critical to review where instruments are located to be sure they're capturing information where we think there may be a problem. There are a lot of traditional tools in the toolbox to aid in monitoring dam performance. It is important to review the tools we're using to be sure that they are the right tool for the job. Sometimes we need to change the tool to capture the type of data we need at the frequency that we need it. Here's an example of a traditional surface survey monitoring approach. Survey monitoring points are spatially distributed across this dam shown in the bottom right. These locations were made accessible via an access bench. This level of monitoring may be appropriate for some projects with low risk of instability or internal erosion issues. However, for a project with these concerns, a higher density of monitoring points may be needed, but with added points, there is an added cost that could be difficult to maintain the required frequency of data collection. For projects with a need for higher resolution of data and higher frequency data collection, such as those with higher risk or high risk of consequences, or those that have a need for large area coverage or difficult to access, other methods may be required. Technological advances in surface monitoring are available and in other monitorings as well, and they've been deployed at a variety of U.S. Army Corps projects. Examples include LiDAR, INSAR, and photogrammetry. Depending on the project risk, the appropriate tool is implemented. On this slide, there's a view of into an area being excavated where photogrammetry was used. On the right is a project where satellite-based synthetic aperture radar was used. In this project to the right, over 200 alignment surface survey monuments were on the project, but only the ones in the area of interest. There was only one that showed any sort of movement, but with the INSAR data used, we were able to detect a higher density of data and detect movement that otherwise would have gone unnoticed. There are a variety of tools and field measurements, and these can be manual or automated. It may be a small data set or a large data set, but in any case, there needs to be a defined, efficient way to get the data from a point of measurement to a long-term storage location where it can then be processed and plotted and readily accessible to the people who need to evaluate the data. Ideally, the data will be able to be visualized along with the site information model information. USACE has inventoried over 70,000 instruments across their projects used for performance monitoring. With that size inventory comes a large volume of data. Most projects have over 50 years of historical data, and many have automated data providing for a huge amount of information that needs to be managed. Here are two dam examples showing the number of instruments and volume of data. Wolf Creek collects over 40 megabytes of data per year, while Percy Priest collects about 51 megabytes per year. Wolf Creek is considered to have a relatively robust amount of monitoring and above average amount of data. But Percy Priest is considered an average sized dam with an average amount of data. To address the growing data management needs for instrumentation data, USACE implemented a monitoring instrumentation data acquisition system. This is a centralized national cloud-based system accessible to USACE employees with permissions to view the data. The product was USACE owned, developed, and managed, and this was determined to be the most cost-effective and appropriate path for the Corps of Engineers. All projects with instrumentation data are within the system and searchable. Here's an example of a search result for a project. When the project is selected, additional information can be accessed. Information includes a variety of data, including the type of instruments at the project, the status of the instrumentation, and various instrumentation groups that have been defined for the project. Selecting an Explorer tab then takes you to an aerial view of the project. This aerial view is interactive, and you can zoom in and out and select particular areas of interest. Instruments are selectable in any grouping, and data plots are readily accessible. The plots are also interactive, allowing for varying the time frame and the scale of the plot. Reporting functions are also built in to allow for custom plotting of the data. Once the data is in data management system, it can then be combined with other available site information data to best evaluate the project data. In the top image, a contour plot was made of all the piezometers that are screened within a particular zone of interest and are displayed in the GIS model overlay. Areas of high and low pressures can readily be identified. The location of instruments in relation to project features is also visible, and the area where the data interpolation is made can be identified between the points of instrumentation locations. The bottom plot is a profile view of the project showing piezometer readings overlaid on the geology. From this plot, the location of the screened interval is readily able to be understood, along with the pressure distribution across the dam foundation at given periods of time. Additional project information such as boring logs, water pressure test data, barrier wall construction data, etc. can be overlaid in either of these two plots to help aid in project performance understanding and risk assessments at different points of time and at different loading events. In short, the U.S. Army Corps of Engineers has a large portfolio of projects. To help prioritize our portfolio, risk assessments are performed. Access to information to make risk-informed decisions is critical. Proper data management aids in ease of access of the data. Tools are available to aid in visualization of the data for a comprehensive understanding of that data. The use of both databases and GIS aid in visualization and help with communication of project risks and performance evaluations. Thank you for your time today.